Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to talk about matrix multiplication. And when I say matrix multiplication, I'm saying when I have a matrix and I multiply it by another matrix. So we're going to review that. I'm pretty confident that most people watching this have multiplied matrices at some point in the past. But even if not, we're going to review it as if you have never seen it before. And we'll get a little practice with it. And then I'm going to talk about multiplying n-tuples together. And you'll see how really it's just an extension, and in fact you've probably done it before without even realizing it in some of your other courses. So I'm going to try to tie everything up into a bow at the end. So just try to get through it with me and see how I conclude this lesson to see if I've done a good job at that. So if I want to define the multiplication of two matrices, I'll have matrix A multiplied by matrix B. Normally in matrix algebra we do not write a dot between them. Just like in algebra, you can have xy or AB, that means A times B. Well, same thing here. We have matrix A times matrix B. But this multiplication in terms of linear algebra, in terms of matrices, is defined only if the following thing is true. The columns of matrix A is equal to the rows of matrix B. And that becomes obvious when you learn how to multiply these things together, but I'm writing it out in words so that you have something to anchor yourself to in the beginning. But as you get more practice, when you try to multiply things together and you know how to do it, you'll realize when it doesn't work. And the case when it doesn't work is when the columns of matrix A do not equal the rows of matrix B. So let's say I have matrix A and matrix B. And so this could be matrix A. Matrix A would be 2, 1, 0, 1, 1, 1, negative 1, 4, 3. This is a 3 by 3 square matrix. All right, and we're going to call this matrix A. All right, now we're going to multiply it by another matrix, which I'll do in red here. All right, and matrix B will be 1, 1, 0, 1, negative 1, 3. So this guy in red here is matrix B. We want to multiply these things together. Now, first of all, notice that the columns of A, we have 3 columns of A, and the rows of B, 3 rows of B are equal. So because the columns of the first matrix are equal to the rows of the second matrix, that allows the multiplication to proceed. In fact, if we switch these things around and try to take B times A, it doesn't actually work out. If you actually kind of pretend for a second that this one was over here, and then we were multiplying this guy times the purple matrix if we moved it to the other side. The columns of the first matrix is 2. The rows of the second matrix, if we moved this over here, the rows would be 3. So the columns of the first and the rows of the second don't match. So we actually can't do the backwards multiplication. And that's kind of the biggest thing. I'll just take a quick aside to make sure to drill into here. Is in all of your math up until this point, multiplication didn't matter if you reverse the order. 3 times 4 is the same as 4 times 3. Negative 5 times 2 is the same as 2 times negative 5. When you go into algebra, x squared times y is the same as y times x squared. But in matrices, that's not necessarily true. Occasionally, for special matrices we'll talk about later, you can flip the order of the matrix multiplication and you get the same result. But in general, you don't, okay? And in some cases, it's not even possible. So sometimes you can flip the order and get it and actually be able to do the multiplication. You may or may not get the same answer, right? But in some cases, you flip the order of multiplication and you can't even do it at all because it's not defined. So always when you're writing a matrix algebra, multiplication, or some kind of relation involving multiplication, just be careful. The order in which you write it down, the multiplication, is going to matter with matrices. So here's matrix A, here's matrix B, and we're going to say that that's equal to some matrix C. So we're going to do this multiplication. The product is, we're going to call it a new matrix called C. And we're claiming that this is possible because of this rule up here. Now what I want you to remember, and what I've taught in my matrix algebra course, is I can write down an equation that describes matrix multiplication. If you look in a linear algebra book, it's probably written out in a bunch of subscripts and showing you how to do it. But basically the way to remember it is over and down. I want you to actually say it a few times. Over and down, over and down, over and down. That's how you multiply. If you remember over and down, then you will know how to multiply matrices together. So say it to yourself, over and down. And that's why the columns of the first must equal the rows of the second. Because what we're going to do is we're going to go over this direction, turn, and go down this direction. Notice how we have 1, 2, 3 elements? 1, 2, 3 elements. As long as we're going over and down, we're always going to have 1, 2, 3 elements, 1, 2, 3 elements, and that's what allows us to do this multiplication. So the way we actually do it, we say matrix C, which is the product here, is we start at the first row of the first matrix and we go over and down, and we take each element times, so here it'll be 2 times 1, and then we'll go 1 times 0, and then it'll go 0 times -1. So what we're doing is going through these columns and down these rows, multiplying the first elements, the second elements, and the third elements, and then we add them all together. So the way we write it down is 2 times 1 is 2, 1 times 0 is 0, 0 times -1 is 0. So the sum of this guy, we both multiply the elements and we add them together, is going to be what's going to reside in that spot of the answer matrix. All right? Now let's kind of go down here into this guy here. So now we go down a row, we go over and down again. So 1 times 1 gives me 1. 1 times 0 gives me 0. 1 times -1 gives me -1, like that. And then we go down to the third row, again, over and down. So -1 times this gives me -1. 4 times 0 gives me 0. 3 times -1 gives me -3. So what I've done here is to create the first column in my answer matrix, the product matrix, I basically go over and down, over and down, over and down. So I'm working through the rows here, creating the rows of the answer matrix, but again, each time going over and down, operating as we see here. Now that we've gone as far as we can get, we've gotten to the end of the matrix here, there's nothing else to do, we can't go down anymore, so now we begin doing the products for the second column over here in the answer matrix. So again, we go over and down, but now we go down the second column. 2 times 1 gives you 2, 1 times 1 gives you 1, 0 times this gives you 0. Again, we're adding everything up as we go over and down. Now we move to the next guy. 1 times 1 gives me 1, 1 times 1 gives me 1, 1 times 3 gives me 3, again adding everything up. Finally, we go to the third row, over and down. 1 times -1, -1. I should say 1 times -1 times 1 gives me -1. 4 times 1 gives me 4. 3 times 3 gives me 9. Now there's nothing else to do. You stop doing the multiplication when you're done, because we've gone over and down, over and down, over and down. So we've gotten to the end here. Now we go to the next column and go over and down, over and down, over and down. Once you've covered all the combinations of over and down, you're finished. All right, there's nothing else to multiply. So then matrix C is going to be equal to, this is going to be 2, this is going to be 0, this is going to be -4, this will be 3, here we have 3, 4, 5, so we have 5 right there, and then here we have 3 plus 9 is 12. So here we have 2, 3, 0, 5, -4, 12. This is the answer matrix C, which is the product of A and B. All right, again, the secret to matrix multiplication is over and down, and you have to kind of get that muscle memory, for lack of a better word, handy. So I suggest that you practice this yourself. We're going to do a few more here in a second as well, but practice these that we do ourselves, practice some additional ones from whatever book you're using, and get some practice with that. You need to master the over and down. Basically, you're multiplying elements, but you're summing them up to get the new guy here. Now, if you look at a matrix algebra book or a linear algebra book, the way that you multiply matrices can be written out in terms of indices of elements. You know, I can define matrix A, matrix B, and I can write a giant sum to show you how to add, to basically form the elements. But ultimately, if you just remember over and down, 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 then you're going to get the right answer every single time. All right, and again, we've already said that if we reverse the order, it's not going to work at all. Let me show you how that, in fact, might be the case. Let me give you, just for variety, we'll try to multiply different matrices together. So 1, 2, 3, 4. This is a 2 by 2 square matrix, and let's say we're asked to multiply it by this. Let's say you have 1, 1, 3, 2, 4, 1. And let's say we want to multiply these together. Well, first of all, originally we said the columns of A have to be equal to the rows of B. The columns of A, that's two columns. The rows of B is 3. So we have 2 columns and 3 rows, so according to our rule, we're not able to multiply them. But even if you forget the rule, even if you don't even know the rule or just forgot about it completely, if you tried to do this, it wouldn't work. Because if you go over and down, you have 1 times 1, 2 times 3, you have nothing to multiply the 4 by because you don't have enough columns here to multiply by the number of rows you have there. And now you can see why the number of columns and rows have to be equal, because you're going over and down. You're cutting through columns and cutting through rows, so you have to have one-to-one correspondence. So this thing is not possible. Not possible. Period. You just can't do it. It's not defined. All right. So we have a few properties of matrix multiplication. Multiplication of matrices. All right. I'm going to write them down. A lot of them are obvious, but some of them aren't. I'm restating a lot of what I've already said, but it's so important for you to understand these properties. They're so central to everything that I want to make sure you get them. So the product AB, 2 matrices, A times B, is not always defined. And that's exactly what we already just said a minute ago. In this particular case, the matrix A times the matrix B is not defined. So when you are writing something down or looking at a proof or whatever, and sometimes they may tell you this matrix multiplication is not defined, now you know why. It depends on the dimensionality of the matrices. All right, let me switch colors. Let me go to black. All right, if AB is defined, in other words, if the multiplication is defined between 2 matrices A and B, then AB is not always equal to BA. In other words, I can take AB and then I can get the answer to that multiplication. And then I can flip the order of the multiplication and do that, and then that is not always the case. And if you think back to the properties we studied in a couple sections ago, that was called the commutative property, whenever you can flip the order and the order of the operation doesn't matter. In matrix multiplication, the order is critically important. It always matters. And when you flip the order of multiplication, you are not guaranteed by any measure to get the same answer. And it just comes about because of the way we define multiplication. So let's do one of these and just kind of prove it to you real quick. Let's say we have matrix A. 1, 2, 3, 4. So quick 2 by 2 matrix, and we're going to multiply it by 1, 1, 0, 1. So here we're calling this matrix A, this is matrix B. Let's quickly just do this math here and do that product. So we're going to go over and down. So 1 times 1 gives me 1, 2 times 0 gives me 0. So when I add them, it doesn't contribute. So I have 1 times 1 giving me 1, right? And then we go down here, go over and down. 3 times 1 is 3. 4 times 0, 0. So what I'm going to get down here is just simply 3 when I add those together. Now I can't go down any farther, so let me go over and down in the second column. 1 times 1 is 1. 2 times 1 is 2. When I add them together, I'm going to get a 3. And finally, I'll go over and down. 3 times 1 is 3. 4 times 1 is 4. Add those together, I get a 7. So here's what I get, the product of these 2 matrices, 1, 3, 3, 7. Now let me flip it around. Let's say these exact matrices I'm going to multiply again. 1, 1, 0, 1. But now I'm going to flip the order. 1, 2, 3, 4. Now in this case, because they're square matrices, 2 by 2, I am allowed to flip the order of the multiplication because I have the same number of columns here as I do rows there. So it is defined, but whenever I do it, you'll see that we're not going to get the same answer. When I go over and down, 1 times 1 is 1. 1 times 3 is 3. You add them together, you're going to get the number 4. Going down here, 0 times 1 is 0, 1 times 3 is 3, so we add those together, you get that. Here we go this way, 1 times 2 is 2, 1 times 4 is 4, and whenever I add those together, I'm going to get a 6. And then going this way, I'm just going to get the number 4. 0 times 2 is 0, 1 times 4 is 4. So this is the final matrix, and you can see that this guy is not equal. Right? And not only are they not equal, they're not even close, all right? So this matrix, I mean, I mean, the number 3 is the only thing that's really in common. It's not like a mirror image or just in some things are in different places. It's a completely different answer. And it comes about because of the sort of complicated way in which we cut across and go down. If you start flipping the order of the matrices, you're switching rows and columns and all your additions and multiplications are totally different. So if you flip the order, and if it's defined, you're very likely to get a different answer. Some cases, for some matrices, you will get the same answer. We'll cover those later. But those are kind of the exception. Most of the time, AB is not always equal to BA. That's what we have found right here. Okay. Another property I want to share with you before we finish this little part here is matrix A times BC, right? If it's defined, let me go ahead and do it like this. What I meant to put is this. If this product is defined, right, then A times BC is equal to AB times C. So what this is saying is that, notice how we have to put a qualifier. If this is defined, because some matrix multiplication isn't defined, if the rows and columns don't work, that's what that means. But if it is defined, then if I take matrix B and C and get the answer, and then I multiply by matrix A on the left, okay, I can do that, and it's going to be the same thing as if I multiply A and B first, and then multiply by matrix C. Notice I have not flipped the order of A, B, or C. Everything, it's A, B, C, A, B, C. Everything's in the same order. It's just that whichever pair I do first is going to give me an equality there. That's something I'm not going to prove to you. It's something that's true, and you can go grab a few matrices and verify that that's the case. So if this triple product is true, then I can put the parentheses around whichever pair I like and get the same answer. One final one I'll share with you real quick as far as properties go. If matrix product AB is defined, if this is defined, then if I multiply a scalar times the product of AB, the matrices A and B, it's the same thing as taking the scalar times matrix A and then multiplying by B, which is the same thing as taking matrix A times the scalar times matrix B. So what this is saying, notice that K is a scalar in every case. And notice the order of A and B. The matrices are always in the same order. I have AB here, and AB here. Those are all in the same order. What it's saying is if I have multiplying by a scalar in addition to matrix multiplication going on, then where I multiply by the scalar along the way doesn't really matter. I can multiply it out after I've done the matrix multiplication, or maybe in between in different orders, but that scalar multiplication doesn't really affect things too much. The biggest thing on this page I want you to know about is these two guys right here. When you have AB, it's not always defined. And if it is defined, if you flip the order, you're almost never going to get the same result unless you have special case.